Hey everybody, welcome back to another round of physics, and yeah, let's get going. The video today, I need to discuss a couple of different mathematical ideas that will be particularly useful moving forward in the course. And the idea, namely, well, the first one that I'll introduce is what I refer to as polar coordinates. Now, up until this point in time, we have been using what is referred to as the Cartesian coordinate system. The idea that we have a direction in the x, y, and z. And our vector triplets, when we quote them, are given in that format. Now, as we further go on in the course, we will sometimes find that different objects, different shapes that we deal with are not easily expressed in the Cartesian coordinate system. It might make the math more, for example, difficult. If we have integrals to do, they become particularly arduous. And so that is how part of the rationale for introducing alternative ways of identifying both locations in space, but also describing shapes of objects. Now, we won't go completely into the three-dimensional coordinate systems at this point. Of course, Cartesian, that is 3D. Or more often when we start out in physics, we just deal with the XY plane and we forget about the out-of-plane component, the one that's out of the page or into the page. And similarly, we will start off here with a two-dimensional coordinate system that I will refer to as the polar coordinate system. Coordinates. And in particular, I will superimpose it on the Cartesian coordinate system. So for example, I will go ahead and draw a y and an x. So we're doing 2D space for right now. And the polar coordinate system is simply, again, a set of numbers that can be used to indicate a location in space. But rather than thinking about walking along the x direction some set distance, and then walking in the y direction some set distance to get your location in space as x and y, the polar coordinate system uses two different numbers, namely how far from the origin you are and at what angle with respect to the positive x-axis. Now you can see, first of all, let me draw the position vector. Okay. And you can probably see right away that the x and y components in the Cartesian coordinate system can very easily be changed into the coordinates required for the polar coordinate system, namely the distance from the origin and the angle that it makes with the x-axis. Go ahead, do it real fast. You go, yeah, and that's a common feature. It is not some mysterious thing. Generally, you should be able to go from one coordinate system to the other via some, I don't want to say simple, but straightforward geometric relationships. So, for example, excuse me, you already know the distance from the origin, that would be the hypotenuse, if you will, of this triangle. And so you can say, hey, the distance from the origin is simply the x component that I already have, the y component that I already have, and square rooted. Similarly, you know that the angle can be found simply by taking the inverse tangent of the opposite over the hypotenuse. Excuse me, opposite over adjacent. Turn my brain off there for a second. And so that in itself should be sort of familiar, sort of comforting. We've been dealing with that through the whole process of vectors. But again, it's just a different way of specifying a location on the 2D plane. So, for example, maybe I should run a couple of example problems, but let's pretend for a second. Again, I'll put the Cartesian coordinates here. Okay. Let's say that we're dealing with, I don't know, a location right here in space. Let's give it the coordinates, I don't know, -5, -3. Okay. Go ahead, take a second, see if you can come up with the polar coordinates for that location. And I just pulled those out of my head. I don't know. But you can say right away, okay, well, the distance from the origin to that point should simply be 5 squared. I'll put the negative sign in for completeness, plus the -3 squared, square rooted. And so you get something like the square root of 34. 25 plus 9, whatever that value is. I'm not as interested in that. The thing that I'm more particularly interested in is thinking about the angle, because we have to be careful with tangent. Okay. So you say, wait a minute, what do you mean, Greg? I know how to do the angle. That is the tangent inverse of the opposite divided by the adjacent. And we're done. And here is where the caution is. Please be careful. Tangent is unable to distinguish between having both components being negative and both components being positive. What I mean by that is you see that we have a negative divided by a negative, and so the inverse tangent of -3 over -5 will give you the exact same angle as the inverse tangent of 3 over 5. Now, of course, you can see how those two angles are related. It's just helpful to keep that little back of your mind. Okay. So you can see that this is 180. So tangent will give us, I'll call this angle theta. And what we're interested in is actually 180 degrees plus theta. Now, again, that is just for reference. Another piece of information that we have to remind you of. So there's just simple, here's how we do the polar coordinate system. Also bear in mind, positive angles are measured with respect to the positive x direction, and we go counterclockwise. So if you're doing an angle clockwise from positive x, then that angle will be quoted as being less than 0. Okay. If you're doing it counterclockwise, then the angle will be greater than 0. Again, just some little things to just be aware of in terms of when we deal with polar coordinates. Another thing to be aware of, and this will apply for polar coordinates, it will apply when we go into 3-dimensional coordinates. Okay. How do we measure angles? This is always good to remind yourself, because we have two different systems. One system, and I would have to double check where this comes from. Maybe it comes from the Babylonians. Okay, I assume that this comes into play because, you know, the Babylonians, that's where we get like 60 seconds in a minute, or 60 minutes in an hour, et cetera, et cetera. But I also believe that this is where we get 360 degrees in a circle. Okay. 60 in particular is what's referred to as a highly composite number. It has a lot of whole number dividers. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and of course 60. So I'll have to double check, but I believe that our circle having 360 degrees comes to us from ancient Babylonia. However, that is not particularly useful for dealing with circles. There is another way of measuring angles, which, as a student of physics, having passed through a semester, you're probably already familiar, you should be aware of, forget about the probabilities, is that we deal in radians. And when we measure angles in radians, there is a nice relationship between the angle that we're measuring the radius of the inscribing circle and the arc length. Good. Just pause for you to come up with that. But you remember that when theta is in radians, then the angle times the radius of the circle is equal to our arc length. And we use this idea a lot when we're talking about rotational motion. The idea that a displacement in space, so if I had an object moving along that arc, a displacement in space is related to the inscribing angle. Now, as we move further, the polar coordinate system, the other coordinate systems, cylindrical, spherical, they are better suited for measuring angles in radians. So from this point onwards, when we're doing angles, I'm going to be working in radians. You might as well get used to it. It makes your life a whole heck of a lot easier. Let's go ahead and do something that we theoretically already know how to do. Okay? And I'll do it in the very calculus way because it's always good. I'll do something that we already know the answer to, but I will solve it in a way that you have seen in calculus, but just to refresh you. So what do I do here? I am going to, let's pretend I want to find the length of a quarter circle. So I have a ring of radius r, and I cut it into 1/4, and I want to find the length of that arc segment. And of course, you say, well, duh, Greg, I already know how to do that. The circumference of a circle, the circumference is given by 2 pi r. And since I have 1/4 of the circumference, that means I have 1/4 of 2 pi r, or alternatively stated, I have 1/4 a 90-degree angle times my radius. And I agree, that's it. Okay. What I want to show you is how could I get that arc length using calculus? And I will do that calculus in 2 different coordinate systems. I'll do it in the Cartesian coordinate system, and then I'll turn around and I'll do it in the polar coordinate system. Okay. So first off, now finding the arc length of a function is a general thing that you often do in calculus. And let's pretend for a second I zoom in on a very, very tiny piece of that arc length right here. And I zoom in, and what I will get is, first of all, if I zoom in enough, rather than it looking like a curved arc, it's now going to look like a straight piece of line. Infinitesimally small, but a straight piece. Okay? And the first thing is that we notice that it goes a distance delta x in one direction and delta y in another. Remember, I'm dealing with infinitesimally small segment. And the question then is what is the length of that infinitesimally small segment if I know it is a width of dx and a height dy? Yeah, good. And you should recognize that the length of that small piece is simply dx squared plus dy squared, and then square rooted. You're just applying the Pythagorean theorem. It's just that now you're dealing with an infinitesimal width and infinitesimal height of this infinitesimally small triangle. Okay. Now, if I want the entire arc length, I don't want just that little segment that I've picked out. I want the entire arc length. What I need to do, well, you could say, well, I'll take the sum of all the little hypotenuses, okay, and add them together. But because I've made these infinitesimally small hypotenuses, rather than doing a summation over finite size pieces, I need to do a summation over the infinitesimally small hypotenuses of all these triangles. Well, I have an expression for the hypotenuse. The hypotenuse is simply the square root of dx squared plus dy squared square rooted. Now let's go ahead and do a little bit of, for lack of a better term, fancy math. Okay? And by fancy math, I mean I am going to remove a common factor of delta x. Don't forget, these are physical, we can treat these like algebraic quantities. In other words, you could imagine, excuse me, a little too much coffee there. You can imagine I'll take a dx squared out, and then I have a 1 plus dy dx. Now, of course, oops, excuse me, first of all, I better square that sucker. And then I take a square root of this whole thing. So I took out the common factor of dx. Well, what I have then, because I have a dx squared square rooted, I can rewrite that as simply 1 plus dy dx squared square rooted times dx. Now for the next bit. We notice that this second term, and this is, you've seen this in calculus before, you notice that this second term is essentially what we would refer to as a derivative. It is the change in y with respect to x. So first off is that we need to find the relationship between x and y for a circle. So an alternative phrase would be, what is the function that describes a circle? Yeah, good. You got it? Yeah, good. You say, I know that. The equation describing the shape of a circle is the radius of the circle squared is equal to the position x squared plus y squared. Why don't I go ahead and solve for y? And I'll go ahead and take the square root while I'm at it. Now the issue is I need to take a derivative of this expression to see how y changes with respect to x. Go ahead, take a minute, pause the video. Okay, you got it? I'll go ahead and write out everything explicitly here. We have the derivative of r squared minus x squared to the 1/2. And the first thing that we notice is that we need to apply a power rule. And the power rule states we take the power, we move it down in front and decrease the power by 1. And so what we end up with is something that says 1/2 times r squared minus x squared to the negative 1/2. But we're not done yet, because you notice that we have a function inside a second function. And so we first apply the power rule, and the second piece that we have to worry about is we have to do the chain rule. We have to take the derivative of, we've already taken the derivative of the outside function. Now we have to worry about the derivative of the function inside. So I've explicitly written that out for us. Well, now you realize that we have another power rule to apply. Now r, very careful, how does the radius of the circle change according to x? Good. It is constant. The radius is a constant value, and therefore it does not change with respect to x. In other words, the derivative of the radius is 0. So we'll go ahead and apply the chain rule here. I have 1/2 r squared minus x squared to the negative 1/2. And I'll explicitly write out we have 0. That's the derivative of r with respect to x. And then minus, again, we have a power rule here. We have a 2x. And we're done. Well, I mean, we still have to, let's simplify. So we see that the change in y with respect to x is equal to, well, that 1/2 cancels this 2. And we end up with something that says negative x over r squared minus x squared square rooted. Pause the video, rewind if you need to, double check that that makes sense in your head. Now, returning back to the original problem, we are interested not in dy dx, we are interested in dy dx quantity squared. The change in y with respect to x, and then we square that quantity. So I'm actually going to be dealing with x squared over r minus x squared. Good? Okay. Now let's go ahead and return back to the problem that we were trying to solve. We said that the arc length for the semicircle is equal to the summation of all those infinitesimally small hypotenuses. And we had the expression 1 plus dy dx squared square rooted times dx. But now we have an expression for how y changes according to x, and we can substitute that in. 1 plus x squared over r squared minus x squared square rooted dx. And why don't we go ahead and simplify this expression? Generally, it's a good idea to find a common denominator. And we note that when we find a common denominator, we have r squared minus x squared over r squared minus x squared plus the quantity x squared over r squared minus x squared. And we notice that, hey, that minus x squared cancels the positive x squared. So we're left with an expression of r squared over r squared minus x squared square rooted dx. What should we do to solve this integral? And again, when you see some sort of integral where you have squareds and square roots, that generally screams some sort of trig substitution, particularly when we don't have powers of x anywhere else in the integrand. So to remind you how we'll set up a trig substitution, well, I always have to draw out a triangle. That's just me, but I'm thinking about a theta. The hypotenuse of the triangle, the longest distance that we're considering in this problem is r, the radius of the circle. X just naturally feels like the horizontal one, and so the opposite side would be given by r squared minus x squared square rooted. Okay. Good. Okay. Well, let's see here. We can immediately see that something like the sine of theta is equal to the opposite, r squared x squared, over the hypotenuse. Something like that. Okay. And so you can see that mimics what the integrand actually is, just that we'd have to do the inverse of that relationship. What else do we have? Well, I can see that the cosine of theta is going to be equal to this x divided by r. Now, this second expression, I've written it down because not only do I have to replace the integrand, I can see that that can be replaced by 1 over sine of theta. Okay. But in addition, I have to replace delta x. Okay. So let's go ahead. Well, if I take the derivative of this second expression, the derivative of cosine is, yeah, very good, sine, negative sine. So I have negative sine d theta dx. Now the upshot for using cosine is that on the right-hand side of this expression, you notice that r is a constant, x is the only variable present. There's no chain rules, there's no product rule, nothing like that. And so I can write on this other side 1 over r. Well, now let's go ahead and get dx by itself. Right? So I move the dx to one side, the r to the other side, and I end up with something that says r, negative r, sine of theta d theta equals dx. Well, that's awfully convenient, right? So let's go ahead and substitute that expression into my integral. And at this point you go, oh, that's nice, goody goody, right? You notice that the sine of theta in the numerator cancels the sine of theta in the denominator. And I end up with something that says negative r, the integral of d theta. Or if you prefer, right, we have to go ahead and we have negative r times theta. Pretty cool, right? I'll go ahead and I'll just go ahead and convert theta back into terms of x. Namely that this is negative r, the inverse cosine of x over r. Okay, using this relationship that we previously had. The last thing is we need the limits of integration from 0 to r. So we go ahead and plug everything in. We have r inverse cosine of 1 minus, excuse me, we'll put this in parentheses, minus the inverse cosine of 0. So what do we have? We have s is equal to negative r. Well, the inverse cosine of 1 is 0. And the inverse cosine of 0, yeah, good, is pi over 2. And you notice now that the negative sign and the negative sign cancel, and we get that the arc length for the quarter circle is given by pi over 2 times r. It's like magic, right? Maybe? Pretty cool, right? Oh. Okay, now we already knew that result, but it's always good that we can use the calculus to get at it. Okay, but let's go ahead and now let's consider a different way to think about the problem. Now, previously when we were dealing in Cartesian coordinates, we said, okay, well, here's the quarter circle, and we pretended to zoom in on it so that we basically, instead of seeing a curved portion, we can think of it as a straight line. And then we went ahead and applied our Pythagorean theorem to actually figure out what the value is of that little tiny line segment, and then we added them all up. Okay. Well, there's a secondary way we could go at it, and this second way just uses the polar coordinates. So you can imagine for a second that I start out at some angle and I have a tiny infinitesimal change in the angle, an infinitesimal change that I'll label as d theta. Okay. And then the question is, what is the infinitesimally small arc length that corresponds to this infinitesimally small angle? A different way to say it, how do I relate the arc length to an angle? Yeah, good. Hopefully you see, and this is the power of using polar coordinates when we're dealing with circular objects. Namely, the idea here is that the infinitesimally small arc length, ds, is equal to the radius of my circle times the infinitesimally small change in angle. So if I want to know the total arc length, I simply need to add up all of these tiny infinitesimal arc lengths. And notice, what does my angle start at with respect to the positive x-axis? Yeah, good. My angle starts at 0 and it goes all the way up through 90 degrees. And notice, we didn't have to do any trig substitutions. We didn't have to do any Pythagorean theorem. We didn't have to do any extra derivatives and all this other stuff, right? All we had to do is say, wait a minute, there's a better coordinate system for us to do this in. You say, wait a minute, r is a constant, so we can pull that out of the integral. And of course, the integral of d theta, that's just simply theta. So the total arc length is given by r, and we evaluate at the upper limit minus the lower limit. And again, we get agreement that the length of the quarter circle is given by pi over 2 times r. Go ahead, review that, mull it over, but it's like I said, it seems almost unfair that one derivation takes like 4 slides and has a bunch of other trig substitutions and everything. And the second derivation says, hey, you know what the arc length of a circle is, and in that coordinate system, it's like, what, 3 lines, and the simplest integration that you could probably imagine, okay? I think that's enough right now. That's a pretty long video. I apologize for that, but it's some good ideas. I'll have a second video giving us more examples, doing it in the polar coordinate system. Maybe we'll do some area calculations. Maybe we'll do some more arc lengths, that kind of thing. But in the meantime, I would say keep up the good work. Bring any questions that you have, and I'll see you next time.